a lecture on integrating and differentiating vectors. It is just a brief lecture and discusses some of the finer points of problems 1 through 5 in the Chapter 2 homework. It is not a comprehensive lecture on integration and differentiation. You can find that in both the text by Stewart and Thomas and also in the written lecture notes. So basically, to integrate or differentiate a vector, you integrate or differentiate each component. But when you integrate, you will end up with constants of integration. Each component will have its own constant of integration. This occurs frequently when we're looking at the motion of a particle or an object. So say we have the acceleration and we want the velocity. Well, the acceleration is vector quantity. In this case, for example, 12 sine t in the I direction plus 3 e to the 6t in the j direction plus 4 t to the 9th in the k direction. So for the velocity, we integrate the acceleration. But as we integrate each component, for example, here's our I component of acceleration. I'm going to integrate the I component. I will end up, of course, with minus 12 cosine t, and then a constant of integration for the I component. The same thing happens with the j component. I'm going to integrate 3e to the 6t. I will get 1/2 6t, and then I will get a constant of integration with respect to the j component, and the same thing happens for the k component. To evaluate those constants of integration, we need a value for the velocity at some time. Typically, it's given at the initial time, so we would have v at time 0. So continuing the same example, say we have an initial value of velocity. Remember, initial is always the value at when t is 0. Now let's say it's 2 in the I direction plus 3j plus 5k. Then to evaluate those constants, we equate the velocity at time 0, including that constant of integration, with the value that we have. In that case, c in the component associated with the I direction is 14. Continuing for the j direction, we had 1/2 c 6 times 0, which of course was 6 to the 0. I'm putting in all the numbers here so you can just see where all the numbers go. In particular, I have to put in, and sometimes students miss this, I have to set t equal to 0 in these different components. And that's why I put the zeros there, because sometimes people miss them. Okay, so we have 1/2 e to the 0, which is 1, plus the constant associated with the j direction, and that equals 3 from our initial condition up here. And then we can solve for cj, and the same thing for c with respect to k. Then we can reassemble, and now we have an expression for the velocity given that particular initial condition. So that's the thing to note. You integrate component by component, but each component has its own constant of integration, and it has to be evaluated based on the initial velocity, which is a vector. Now if we want a position, we would just continue integrating. Again, we take that velocity and we integrate component by component, and then we would get the position. Each one of these integrations will, if we want to continue the integration and get position, then we integrate that expression that we had for velocity. And again, each one of these integrals is going to give its own constant of integration. There will be a ci associated with the I component, a cj here, and a ck here. I'm using the same notation that I did for velocity. If you left your ci's in, then you would have a different issue. You'd have to use some other notation. But to evaluate those constants of integration, you would need some value for the position. For example, if you had r at 0 was something, 3 in the I direction minus 10 in the j direction plus 6 in the k direction, you can use that to solve for your ci, cj, and ck. But remember, these are not, this 3 does not give you a value for ci, the minus 10 does not give you a value for cj, and the 6 does not give you a value directly for ck. Instead, you have to take your integral, and then you have to evaluate it at, in this case, t equals 0. So I'll show you that. For example, you've just seen it for velocity, but I'm repeating it here. Say I integrate this, the j component, and I would get, should be 1/12 e to the 6t plus 5/2 t plus cj. and I know its value when t is 0, so I put t equals 0 throughout this equation. Well, e to the 0 is 1, so I'll have a 1/12 here. When this t is 0, in this term, of course, that's 0, and then I have Cj, and it equals minus 10. So now I solve Cj would be minus 10 minus 1/12. Okay? So you have to evaluate your answer at, in this case, t equals 0, and then solve. In some cases, it will be identical, but in general, it's not. And I'll talk a little bit about some parametric equations. There's two parametric equations that you need to recognize. The first is a circle, and the second is the ellipse. If we write the equation for the circle in Cartesian coordinates, we have r, I used capital R for the radius of the circle, equals x squared plus y squared. We could also write it in cylindrical coordinates, alright? But here's the parametric equation for that circle. Right, remember, t is a parameter, and what the parametric equation does is trace out the circle in time. So we have r of t equals alpha. Alpha is going to be the radius times the cosine of omega t. Omega is the angular frequency. It determines how fast the circle is traced out. And then plus alpha times the sine of omega t in the j direction. If you invert the sine and the cosine, you just have a circle going in the other direction. And the way to sort of prove this to yourself is just write a table of values. But instead of doing that, I'll just plot them there for you and show you where they turn up. Now when t equals 0, I'm doing this equation, then r of 0 would be, well, cosine omega t is going to be 0. I mean, it's going to be 1, so I'll have alpha in the I direction, and then in the j direction, 0. That gives me this point on the circle. This is alpha, by the way, and also up here. Okay, now let t progress to where it is pi over 2 omega. You have to throw the omega in here. So when it's pi over 2 omega, the first term, the I term, will be 0, because this will be the cosine of pi over 2, which is 0. This term will be 1. The sine of omega t evaluated at pi over 2 omega will be 1. So now we have 0 in the I direction plus alpha in the j direction, and that is this point right here. Now you can continue on as t changes. You just grab more of these points, moving around the circle. If you have it written like this, your parametric equation written like that, I'm going to change the color here, then the first point when t equals 0 will be up here, and then you will continue in this direction. So this circle is traverse in a clockwise direction. This is in the counterclockwise direction. Now let's look at the ellipse. This is the equation for ellipse, and ellipse in Cartesian coordinates. Here is a parametric equation. It looks just like the circle, except that the amplitude of the cosine term and the amplitude of the sine term are different. Alpha does not equal beta in the ellipse, but alpha is equal to beta in the for a circle. And this is an ellipse is traversing the counterclockwise direction. Here's one in the clockwise direction. And you can see this also by plotting a few points. So I'll look at this equation, and I'll let t equal 0. If t equals 0, the cosine is 1, but the sine is 0. So r of 0 equals alpha in the I direction. So I will be right here. This is I. Here's j. This is alpha. So that's the point on the ellipse right here. Right, now if I move over to where I have t equal to pi over 2 omega, then when I substitute that into the equation, this first term is 0, but sine will be 1, and so r at this value, pi over 2 omega, is going to be 0 in the I direction plus beta in the j direction. So that's where I come up here. And you can continue. So you see how the curves are plotted. But try to recognize this. Recognize this as the equation for a circle and this as an equation for an ellipse. In the homework, you were to look for the maximum and minimum of the speed and the acceleration. So to find the speed, of course, is a magnitude of the velocity, so you have to take a derivative. Not very hard to do. And now you have a vector for the velocity vector. And the magnitude is the square root of the velocity dotted with itself. Now, here is the expression you get. Contrast this with a circle. In the circle, alpha equals beta. So if these are the same, you can factor them out. Then you have alpha squared omega t plus sine squared omega t plus cosine squared omega t, and that's 1 by the Pythagorean identity for trig functions. And so you have alpha omega, which is a constant for the circle. Now, that cannot happen here because you have an alpha here and a beta here, and they're different. So what this tells us is that that speed is changing as you go along the elliptical path. So here's an example. Say r was 60, so in this case, oops, didn't get the pin. Okay. Alpha equals 60 and beta equals 2. So when I take the derivative, I have minus 160 times sine omega t plus 6 times the cosine omega t. And here's the speed along the path, and I'm going to give you a graph of that in a minute. You can see there's a much larger component here. So it's going to vary with t. It's going to kind of swamp out this one, and I made these numbers very different to emphasize the effect. Now we do the same thing for acceleration. We take the derivative of the velocity. Here it is in general. Substituting our numbers, this is the acceleration vector. Minus 450 cosine omega t in the I direction, minus 18 cosine omega t in the j direction. And again, we have a magnitude that is dependent on time. The easiest way to show you what's going on is to show you the graphs. So here is the elliptical path. 60 was the alpha, and when t equals 0, we're out here in the I direction. Didn't get very good labels on here, but this is the alpha, all right? And so when t equals 0, you're at this point. When t is pi over 6, we have to worry about the omega is 3. Then we're up here, and we're picking out these points as we go along in t. But you can see the major axis is going from minus 60 to 60, and the minor axis is only going from minus 2 to 2. Now we'll look at the velocity and the acceleration. Here I've plotted the velocity and acceleration as functions of time. Remember, they vary with time. All right, so the velocity is low at t equals 0, increases, decreases, increases, and decreases, and this is for one trip around that elliptical track. But where the velocity is low, in this case, the acceleration is high. So they're out of phase. And let's patch them up with the picture of the ellipse. These aren't very big pictures, but I think you can see what's going on. Remember, this is time here. So at t equals 0, I'm at this point in the track. At this point in the track, the velocity is low, but the acceleration is high. So when I'm coming into this corner, if I were a race car driver, I would be going, I'm not sure how they drive, but I can't even drive very well myself, so this is not a good analogy. I'll just try to state what I think happens. All right, your velocity decreases, but your acceleration increases in the turn. Now get out here in this flat part. This would be pi over 6. In that case, your velocity is very high, so you've picked up speed, but you're not accelerating very much. That acceleration is low. Go over here to the other corner, your velocity drops again, but your acceleration is high. And now we come into this straight stretch, and we have a high velocity and a low acceleration, and then the cycle repeats.